Protecting groups. Protecting groups are used in synthesis to temporarily mask the reactivity of a functional group towards a particular reagent. Let's say that you have a compound in which there are two functional groups present, functional group 1 and functional group 2, and both of these functional groups are reactive to a particular reagent. But you do not want both of these functional groups to react with a reagent. Instead, you want only one of these functional groups to react. Let's say that you only want functional group 1 to react and not functional group 2. So in which case, you have to protect the functional group 2. This group or molecular framework which has been added to the functional group to hide it from the reagent is called as protecting group. Now, after you make the chemical modification of the functional group, the protecting group will be removed. This is more like tape painting. Let's say that you do not want to paint in certain area of the wall. So in which case, you will mask the area with a tape and then you will paint the entire wall and then finally you will rip off the tape. That is exactly what we are doing here as well. Here are some of the characteristics of a good protecting group. A good protecting group is easily added to the sensitive functional group, and also it is resistant to the reagents which is used to transform the unprotected functional group. And also it should be something that can be easily removed to regenerate the original functional group. Aldehydes and ketones can be protected by converting them into cyclic acetals. For example, when you have an aldehyde or a ketone and react it with 1,2-diol or 1,3-diol, they are going to form the 5-membered or 6-membered cyclic acetals respectively. This reaction right here is exactly the same as what we have learned in the case of acetal. But here, instead of taking 2 equivalents of the alcohol, we'll only be taking 1 equivalent of this diol since we have both the functional groups, both the hydroxy group in the same molecule. Let us see how an acetal or ketal is used as a protecting group in this synthesis. Here is a keto ester because you do have a keto group and also an ester. So this is a keto ester and we wanted to convert this into an hydroxy ketone. So we have an hydroxy group and we also have this keto group. So when you look into the final compound, you can see that the keto group is preserved. Now, so basically this conversion, if you take a look into this conversion, this is basically reduction. Ester group has been reduced to an alcohol. In which case, if you use lithium aluminum hydride, it's going to reduce both of these functional groups. It's going to reduce the ketone to an alcohol. The ketone will be reduced to a secondary alcohol, and this ester group is going to reduce to a primary alcohol. But you do not want this ketone to react with lithium aluminum hydride. So in which case, what you will do is you will protect this keto group using the acetal formation, and then you will perform the synthesis on this ester, perform the synthetic modification on this ester to get it converted into the corresponding alcohol. And then finally, you will deprotect the acetal group. So what happens in all of these reactions is you will first do the protection of the functional group, which you want to hide from the reagent, and then you will do the actual synthesis. Okay, so where you're going to make the chemical modification on the functional group. Okay, and then you're going to do the deprotection, in which case you're going to preserve the functional groups. So let's see how this synthesis is carried out using the protecting groups. So let's write down the keto ester that we have. This is the keto ester. To begin with, you're going to do the protection. So we needed to protect this group. So in which case we are going to use we can use 1,2-diol or 1,3-diol. So here in this case we are going to use 1,2-diol. And this is going to form a 5-membered cyclic acetal or cyclic ketal. You're going to get a 5-membered cyclic ketal, and this step right here is the actual protection. Once you are protected, you're going to do the chemical modification on the other functional group. We are going to use lithium aluminum hydride here in this case because it has the ability to reduce this ester functional group into the alcohol. And in the next case, you're going to react it with dilute acid. With the use of this dilute acid, hydrolysis is going to take place where this acetal group is going to get converted into the original carbonyl group. And this oxygen will be protonated. And then finally, you will also get back your 1,2-diol. While this step right here is protection, this step right here is deprotection. So in synthesis like this, the first step would be protection and the last step would be deprotection. And in between these two, you will be doing the actual synthesis. Aldehydes and ketones react with thiols to give thioacetals and thioketones. Now, this reaction is exactly similar to what we have learned in the case of alcohols reacting with aldehydes and ketones, in which case acetals are formed. The only difference here is instead of oxygen, we are having sulfur. That's the only difference. Thioacetals are extremely useful compounds in organic synthesis because they can be desulfurized in the presence of iron and nickel, where the carbon-sulfur bond is now replaced by carbon-hydrogen bond. Now, this is one way to convert the carbonyl group into methylene group.